Hello and welcome back to Prolumnus. In this video we'll be looking over some properties of derivatives. Now since derivatives have so many different formulae and properties that we can look into, let's jump straight into it. So we'll start off the derivative properties with one of the simplest but one of the most amazing. And that is that the derivative of e to the x is itself e to the x. Now that's really special because other than the trivial function, where x is equal to 0, this is the only function that does this. Now e, if you're unfamiliar, is a constant that equals about 2.7-ish. And it's actually kind of like pi, or it goes on forever. It's a really interesting number, and we'll likely come back to do a video on it in the future. Now the inverse of e is natural log, which means that if you take the natural log of e to the x, you get x back. So they sort of invert each other, just like how the derivative and the integral are inverses of each other. Now, the derivative of natural log is 1 over x, or the inverse of x. The next rule that we'll go over is the power rule. Now this one's really simple. If you take the derivative of any polynomial, so just x to some power, where it would be to some exponential, you take the power and you sort of bring it out front, and you keep x to the same power but one less than it. So that power you just pull out as a coefficient multiple on front, and you leave one less than that. And you can prove this and most of the rest of these using the limit definition, which we may go into in a future video. Though this also implies that the derivative of k being some constant, doesn't matter what it is, it could be 1, it could be 0, it could be 3/2, it could be 16 trillion, is equal to 0 using this rule. Because if that n is equal to 1, that means that that n would be equal to 0, that means that x would be whatever the coefficient is in front of it, which means the derivative of k would be 0. Now if you take the derivative of sine of x, you get cosine of x. And the derivative of cosine of x is negative sine of x. So these two sort of flip-flop, they dance back and forth between each other, and that means that these two are cyclical functions. One of the few that will do that. And then if you do the derivative of tangent of x, it is equal to secant squared of x. Also could be written as 1 divided by cosine squared. That you can prove with the quotient rule, which we will go over in the next derivative video. Now you can imagine this something like here, where if you start off with a sine function like this, then if you do a derivative on it and you plot that derivative at every point, you would get the cosine function. And if you look point for point, you can sort of see that correspondence, where here at this first point, you've got x is equal to 0, and the slope should be about 1. The rise over run is about equal. And here, cosine at x equals 0 is equal to 1. So that checks out. And then you look here at x equals pi over 2, or 90 degrees, and x equals 3 pi over 2, or 270 degrees. You can see that both of those have a slope that's perfectly flat, or 0. Now where does cosine 0 out? Well, at exactly those 2 points. So that checks out as well. So those are some basic derivatives and basic properties that'll be useful. We can move on to some of the rules of derivatives. So one of the most important rules about a derivative is that it is what is called a linear operator. That's just a special term that means if you have something that looks like this, where it's the derivative of m times f of x plus n times g of x, where m and n are some constants, and f of x and g of x are two different functions, that will be equal to m times the derivative of f of x plus n times the derivative of g of x. So all this means is that you can split up these functions into two separate derivatives and evaluate them independently. And it means that you can always pull out constants from the derivative, which are both very useful tools when solving for them. Next, we can look over the product rule, oftentimes written like this. If you have the derivative of some function f times some function g, the result of that is f prime times g plus g prime times f. Now, this little apostrophe notation, used prime, is what you call it, is another way to write the derivative. So d dx of f of x can also be written as f prime of x. Now we can go to the quotient rule, where instead of multiplying them, we are dividing two functions. So we have f divided by g. It's a little bit bigger, but it looks like this, where you have f prime times g minus g prime times f all over just g squared. So all you have to do is basically take this product rule, make sure you add a negative sign where the bottom one is the derivative, and divide by the bottom squared. And these again you can prove using the limit definition, which we will likely go over in future video. Now finally, possibly the most important among these three is the chain rule. Now the chain rule looks something like this, where you have a derivative of a function f composed with a function g. Now this just means that you use g of x, which is a function, as an input for another function, f of x. And the result of this is f prime of g of x times g prime of x. Now, since this was a little bit harder to think about than the other two, since it looks a bit more abstract, we'll use a quick example. So let's say you wanted to take the derivative of sine of x squared. Well, here, your f of x is sine of x, and your g of x is x squared. So f is equal to that, and g is equal to that. So you see that x squared is composed inside of sine of x to get sine of x squared. So that means that this derivative would be equal to, well, we have to take f prime with the same g of x inside of it, so that means we derivate sine to get cosine and keep the x squared inside. Then we multiply it by just this derivative of g prime. And using the power rule, we can see that the derivative of x squared is 2x. So if you take the derivative of sine x squared, you get 2x cosine x squared. And there you have it, all the most important properties of derivatives. Using these as well as the basic derivative from the previous board, you can pretty much solve most of the elementary and intermediary kind of derivatives that you're going to come across in your first few calculus courses. So hopefully that was useful for you guys. If there's anything else you'd like to know about them or any other topics you'd like to see us cover, feel free to let us know down in the comments below. Please like and subscribe, and see y'all in the next one.